So I'm Carl, K9LA, up in Fort Wayne, Indiana, up in the northeast corner of the state. We're about 20 minutes from Ohio and about 40 minutes from Michigan. I should mention that when I worked for Motorola, I started out in Schaumburg, Illinois, the western suburb of Chicago. Then in 1979, I transferred down with Motorola to their facility in Fort Worth, which was on North Beach Street, just a little bit north of the Airport Expressway. That's what I know it as. It's probably got another name by now. A lot of hams in Schaumburg, a lot of hams down in Fort Worth, and we had a good time. It's nice to be able to do stuff outside in the winter, that's for sure. So let's get into the program here. Here's what we're going to cover. We're going to take a quick look at the previous 24 solar cycles, because it's always good to look at history to see maybe if some kind of pattern is developed. Then we'll look at the latest data on cycle 25. We'll talk about the ionosphere and sunspot numbers, and then space weather and propagation. And then I'll kind of talk about what we can expect over the next couple of years on 160 on the HF bands, 80 through 10 on 6 meters, and even 2 meters, just in case. So here's a plot of all previous solar cycles. That's the XL plot, shows the maximum smooth sunspot number of each of the 24 solar cycles. In the annotation in red on the plot, that's cycle 19, the largest in recorded history. So it should be the biggest column, and it certainly is. We had a couple pretty big solar cycles after 19, 21 and 22. They were really good for the higher bands, and it's too bad we didn't have all the HF rigs with 6 meter on them back then. That would have been really a lot of fun. Cycle 23 is interesting because it's, if you take the average of all the 24, it's about an average cycle. And then 24, our last solar cycle, smallest in our lifetimes. You can see that on the plot, unless you lived back to cycle 14, which is probably in the 1800s, and I doubt that. And it's also the cycle 24 is the fourth smallest in recorded history. Cycle 1 began in 1755. That's when it was deemed that the sunspot record was good enough to start. You're probably familiar with the Maunder minimum. That's when we had very, very few sunspots. It occurred from 1645 to 1715. So that's why, well, a big reason why we don't go earlier than 1755, because there wasn't a lot of sunspots to count during a lot of that period. Now, what's interesting about that plot, you can see that the maximum smooth sunspot numbers for each cycle have kind of gone through a cyclic period. We've gone through 3 periods of big solar cycles. For example, cycles 1, 2, 3, 4 were kind of big. Cycles 8, 9, 10, 11 were big. And cycles 17 through, let's say, 23 were kind of big. What that also says is we've been through 2 periods of small solar cycles. Cycles 5, 6, and 7 certainly were small. Cycle 6 is the smallest in recorded history. Cycles 12, 13, 14, 15, and 16 weren't as small as 5, 6, and 7, but they certainly weren't as big as those 3 periods of big solar cycles. So the big question was, is cycle 25 going to get us out of this apparent 3rd period of small solar cycles? Because that's what looks like cycle 24 did. It might have ushered us into a 3rd period of small solar cycles. So I'll just make a quick mention about solar cycle predictions. There were more than 50 for cycle 24. There are more than 50 for cycle 25, and you may want to ask, why are there so many? For both 24 and 25, the predictions went from a small cycle to a big cycle. So again, why so many? Well, we just don't fully understand the sunspot cycle process. We know it has to do with how magnetic fields move inside the sun and how plasma flows inside the sun, but the nitty-gritty details are not yet fully clear. There are many people working on this, and hopefully someday we won't have to have so many predictions for a solar cycle, and we'll kind of get it right. Now, since we have so many different predictions, they compose many different methods to make the prediction. One of the prediction methods that seems to work the best is the precursor. What it does is what you do is look at something before cycle 25 starts, and that may tell you how big cycle 25 is going to be. And one example of a precursor is the length of solar minimum right before the cycle starts. The length of a solar minimum can vary from a couple of years to 4 or 5 years. And that one seems to kind of seems to give us the best idea. Of course, the future is understanding the physics inside the sun. And lots of people are working on that, trying to understand it, but nothing yet. So here's the latest data on cycle 25. That's the thick red curve. I also have 4 other solar cycles on that plot just to kind of show you where cycle 25 is. The green plot, that's cycle 24, the smallest in our lifetimes, 4th smallest in recorded history. That X is the maximum of cycle 24, and you can see it took about 65 months to get from solar minimum to its peak. The orange is cycle 23. Remember, that was the average cycle. And just likewise, that X is the peak of cycle 25. It took, looks like 64 months to get there. Then remember I mentioned cycle 21 and 22? Well, there's cycle 21, December 79 is when it peaked. That's when the X is. It only took 46 months to get up to its peak. And then cycle 19, the biggest in recorded history, it peaked in March of 58. The X is where it peaked, and it took about 47 months. So one thing that's kind of obvious is the faster a cycle rises, like cycle 19 in purple, like cycle 21 in blue, the quicker it gets to its maximum. And the maximum is much higher too than anything else. Also note way on the left there, it kind of depends a little bit on how low a solar cycle is at solar minimum. It kind of looks like the ones that are higher than almost zero are bigger, but that's not a real 100% correlation. So you can't really make too much out of it. Now, right now, cycle 25, the big thick red line, we have 53 months of data. Cycle 25 has surpassed cycle 24. Yay. Okay, that's great. And of course, the question is, will it make it up to an average cycle like cycle 23? All I can say right now is perhaps, keep your fingers crossed. If it does get bigger, then that's good for the higher bands, 15 meters, 12 meters, 10 meters, and even 6 meters. Okay, one question that a lot of people ask is cycle 25 going to have one peak or 2 peaks? You can see in that plot, there's cycle 24 data. The blue is sunspots that emerged in the northern solar hemisphere, the northern solar hemisphere. The orange curve is the sunspots that emerged in the southern solar hemisphere. And you can see what happened is early on when cycle 24 started, the northern solar hemisphere was active. Southern wasn't, but then that flipped towards the end of cycle 24, at least the end of the maximum. The southern hemisphere was very active, and the northern wasn't. The green dotted is just the sum of both the northern and the southern solar hemispheres. You can see a very well-defined, two well-defined peaks there with a nice deep valley in between. So let's move over to the right there on cycle 25. You can see up until a couple months ago, both solar hemispheres were about equal. The number of sunspots in the solar hemisphere, in the southern hemisphere, the number of sunspots in the northern hemisphere were pretty much equal. But the past several months, looks like the northern solar hemisphere is kind of quieting down, but the southern solar hemisphere is getting more active. So we'll have to see what happens. And that brings up the question, that little red arrow, and is this a peak question? Is that considered a peak? And what we're seeing now is a second peak? Well, in my humble opinion, that first so-called peak really doesn't show a well-defined valley. So I don't think it looks like we just have one peak so far. And things may go up and down a little bit, but it's getting kind of late to have two peaks. But with that southern solar hemisphere working and the northern not, we'll see what happens. So my best guess right now is we're only going to have one peak for cycle 25. Some other solar cycles had double peaks, cycle 22 and 23. I'm not sure anybody understands why that occurs, except, we know it's because sunspots don't emerge at the same time in the two solar hemispheres. Why that happens from a physics explanation, we just don't understand that yet. Okay, just a really quick review of the ionosphere. Those are electron density profiles. In other words, the number of electrons, free electrons per cubic meter versus altitude. There are two pairs. One pair is solar min, solar max at night, and the other one is solar min and solar max during the day. The F region, which splits into the F1 and F2 region during the day, has the highest electron densities. You can see that. The peaks occur at the highest altitude. That gives us the longest hops. So what that means is the F2 region is really the most important for our long distance HF propagation. Sure, other modes can give us long distance, but most of the time it's just via the F2 region. Now the E region is the second highest electron densities. Because it's lower in altitude, it gives us shorter hops. Also, the E region altitudes is where sporadic E occurs during the summer, mostly during the summer, which I'll just make a comment. We didn't have much of a sporadic E season this summer. And the D region, that's the lowest one. It can't bend signals, HF signals back to Earth because the number of electrons are just way too low. It's the lowest height, and that's where ionospheric absorption occurs. Absorption reduces signal strength, makes your signal weaker. So that's a quick review of the ionosphere. Now, I've talked about smooth sunspot numbers. You're probably aware that there's also daily sunspot numbers, and there are monthly mean sunspot numbers, or monthly average, and then smooth. Okay, here's cycle 23. The data in red is the daily sunspot number. You can see it's very spiky, and it might be kind of hard to tell what's going on with the solar cycle because all those spikes are in there. So what you can do is take all the daily values in a month and average it, and then plot that. And that's what the blue curve is, the monthly mean or monthly average. You can see a lot of the spikiness has been removed because of the averaging. but there's still some in there, and it could give you a little problem in telling what's going on. So the next logical thing to do would be to average the monthly means, and that's what we do. It's a 12-month running average, and it's called the smooth for an obvious reason. The curve is very smooth, and it's also easy to see that cycle 23 had two peaks. There's a nice well-defined valley in between the two peaks. If you plotted the 10.7 centimeter solar flux, you'd see the same results. The daily flux is very spiky. Monthly mean flux is a little bit better. The smooth flux is nice and smooth. Now, we use smooth sunspot numbers for two reasons. First, it's the best way to see what a cycle is doing, and it's the official measurement of a solar cycle. The maximum of that smooth curve gives us the maximum of the solar cycle, and that gets recorded in history. Also, the smooth sunspot number gives us the best correlation between sunspots and what the ionosphere is doing. We'll talk about that in a little bit and what all that means. Okay, we have terrestrial weather and we have space weather. So what's terrestrial weather? Well, the sun heats our atmosphere, and the result is weather in the troposphere. The troposphere goes from ground level to about 11 kilometers, which is about 30,000 feet. Now, I've seen on flights, airline flights, I've seen thunderstorms topping out at about 70,000 feet. So they can, get up into the stratosphere. But most of our terrestrial weather is below 30,000 feet. Now, in general, terrestrial weather does not affect HF except for QRN, which is noise, on our low bands, 160 meters through 40. Talk about that a little bit later too. So what's space weather? Well, that's stuff that happens outside our atmosphere. It's disturbances on the sun. There are coronal mass ejections, CMEs, when lots of material explodes on the sun and it's sent towards Earth. Coronal holes are just very high speed solar wind coming to the Earth, and solar flares, they can cause problems too. We'll review those three disturbances in a little bit here. Also in space weather, I guess you could call a gamma ray burst, which is a GRB, can come from extremely far away. I mean, we're talking, billions of light years away. Those things can be very powerful because they're a very thin beam of gamma rays, which have very high energy, even higher energy than X-rays. So we can see them from far away. That's for sure. Okay, here's the disturbances to propagation. There are three of them. There are geomagnetic storms. That's what happens when the K indices are elevated. We'll talk about the K index in a little bit. The geomagnetic storm is caused by either a coronal mass ejection or a coronal hole, and it decreases the maximum usable frequencies in the F2 region, which can be degraded for days. The maximum usable frequency is just the highest frequency you can use on a given path at a given time. It has to do with how much ionization is up there, and that can be translated into a maximum usable frequency. The second disturbance is solar radiation storm. We're not real sure what accelerates protons to relativistic velocities or relativistic energies, but we think it has to do with the combination of a flare and a CME. And like I said, that accelerates solar protons in the solar atmosphere, and they head towards Earth very, very fast. It causes increased absorption in the polar cap. That's the area inside the auroral oval. And it results in weaker signals on over-the-pole paths for a day or two. What's an over-the-pole path? Well, that's from, for example, from W5 to Finland to Russia to India. Those go over the North Pole, and they can be affected by a solar radiation storm. The third disturbance is radio blackout. It's caused by the X-ray radiation, electromagnetic radiation from a big solar flare, an M or an X class. It causes increased ionospheric absorption on the daylight side of Earth. The lower frequencies are affected the most. And we have weaker or non-existent signals for an hour or so. So of all the three storms, the three disturbances, geomagnetic storm is the worst one. The other two occur, but either we don't pass over the pole that much as we do normal paths. And like it says there, the radio blackout only lasts for an hour or so, and then the bands are back to normal. Now the gamma ray burst, it's when a huge energetic explosion from a high mass star when it implodes, and it can affect VLF propagation, down where we talk to our subs and all that kind of stuff. And it can cause more absorption on those signals, but it's really a short-term event, probably not more than 10 minutes or so, and it goes away pretty quick. Okay, space weather and propagation. There's lots of data on the internet. You can spend probably years looking at the internet and all that stuff. But there are two general categories that are important for us as hams in relation to propagation. There are solar indices, which tell us the amount of ionization that could be up there in the ionosphere. In other words, what the MUF, maximum usable frequency, could be. The three solar indices that we see the most are SN, the sunspot number, SFI, the 10.7 centimeter solar flux index, and also EUV, which is extreme ultraviolet radiation. Now that's the true radiation of the F2 region. Sunspots and solar flux have nothing to do with ionizing our atmosphere. They're proxies for the extreme ultraviolet radiation. And of course, we can't measure EUV at ground level because as the EUV impinges on its atmosphere, it loses energy as it creates free electrons in the ionization process. So there's nothing left when it gets to ground level. So we have to measure it with satellites above our atmosphere. Okay, geomagnetic field indices. They indicate a possible degradation to the MUF. In other words, if the ionization up at F2 region altitudes is depleted because of the elevated K indices. We have the K index, which is a 3-hour index. It tells us how active the Earth's magnetic field is. So there are 8 of those each day. The K index goes from 0 to 9. It's a logarithmic scale. 0 is extremely quiet conditions. 9 is extremely disturbed. Tied to the K index is the A index. It's a daily index. It's an average of the 8 K indices. It's a linear scale, goes from 0 to 400. 0 is extremely quiet. 400 is extremely disturbed. B sub Z. That's the component of the interplanetary magnetic field. In other words, the sun's magnetic field that is perpendicular to the ecliptic, which means it aligns with the Earth's north-south magnetic field. If B sub Z is a large negative value, that's not good. The F2 region will be screwed up, and So that's a good one to kind of understand if you want more than the K index. SW is the solar wind speed. Quiet time speed's about 400 kilometers per second or less. And if it gets higher, that means there could be a problem. It could screw up the E region, or the F2 region, I'm sorry. And in my humble opinion, we should pay attention to the SFI and the K index. Again, the SFI will tell us what the MUF could be, and the K index could tell us if the MUF is degraded because of a geomagnetic storm. So where do we find those space weather parameters? Well, one place is QRZ.com. There's a banner by N0NBH, and he gives a lot of data there. This one I picked up from QRZ.com homepage. The parameters on the previous slide are in gold boxes. You can see I pulled that 1922 UTC. Take away 1926 that's 1 o'clock p.m. your time today. Solar flux index was 150. Sunspot number was 96. A equals 7, K equals 2. Well, remember that A index goes from 0 to 400 and K goes from 0 to 9. So that kind of says that our Earth's geomagnetic field was kind of quiet. The 3 or 4A, that's the extreme ultraviolet at 30.4 nanometers. It's interesting. If you want to dig into that, you can go download EUV data and see what's really going on. There's B sub Z. It's minus 11.2. What it says is it's not too large negative, so it's not too bad. And that kind of agrees with the A and the K index. Solar wind speed is 382 kilometers per second. So that's less than the quiet time 400 in general average. Okay, also down at the bottom, there's an MUF US boulder. That's a real-time measurement. Okay. And it tells us if Boulder was the midpoint of a 3,000 kilometer path, the MUF would be whatever it reports. Unfortunately, a lot of ionoson data in the United States is not getting reported to the public. I don't know if that's a long-term trend because of some reason or what's going on, but if you go to the N0NBH banner, you'll probably see that there's no report, but that would be a good real-time indication of what the heck's going on. Again, SN, SFI 304A, that A with a dot is angstroms. And they're generally correlated. All of them will be low or all of them will be high. And that'll give an indication of possible degradation to the F2 region. There's also a general correlation between, SN, SFI 304. They're all either low or high, and that gives us an indication of how well the ionosphere could be ionized. And the AK, B sub Z, and SW, that tell us if we really do have that amount of ionization or it's screwed up. Again, if AK and SW are low, that means BZ is going to be positive or small negative, kind of like what we're seeing today, minus 11.2. AK, SW are high, that means the BZ is going to be large negative, very large, minus 50, minus 100, something like that. And that measurement is in nanoteslas. Okay. So if we know today's solar flux and the K index in the 3-hour period, do we know propagation? Unfortunately, we do not have daily propagation predictions. In other words, the SFI and the K index don't give us what exactly the ionosphere is doing right now. And why is that? That's because there are really three sources of the day-to-day variability of the ionosphere. One is solar activity. That's where the SN, sunspot number, solar flux, and the EUV come into play. We have a pretty good understanding of how all that works. The second source of day-to-day variability is geomagnetic field activity. We talked about the K, A, B sub Z, and solar wind. We have a pretty decent understanding. The best model we have of how that affects the F2 region uses the past 11 K indices. So that's 33 hours of K index. That's done because it matters how a storm develops. You can't just use one index, one 3-hour index. That's not going to give you a good answer. You have to use the last 11 3-hour indices. The third source of variability is events in the lower atmosphere that can couple up to the ionosphere. We don't have any parameters for that yet. There's lots of research going on to try and understand that. What are events in the lower atmosphere? Well, we're talking about hurricanes, earthquakes, nuclear explosions, underground explosions. We can see signatures in the ionosphere of that stuff. And what it can do is it can set off a gravity wave that couples up to the ionosphere and can cause a traveling ionospheric disturbance in the F2 region. In other words, the MUF, the maximum usable frequency, is going up and down, up and down, up and down. We just don't have a good handle on all that. So that's why we don't have daily predictions yet. Will we ever have daily predictions? Maybe. Lots of research, and I think hopefully we'll get to understand it better. So what all this means is when you run a prediction with maybe W60L prop or VOACAP, the output is statistical in nature. It gives us monthly median MUFs and monthly median signal strengths. In other words, 50% probabilities. So there could be a range of the MUF and the signal strength in that month you're looking at. And the medians are 50% numbers, so you can determine what the shape of the distribution curve is on both of those parameters, if you want to dig into it that deep. So we can apply the solar flux and the K index to give us some guidelines. For propagation on the low bands, like 160, 75, 80, 60, 40, they're best around solar minimum. And we desire the long-term solar flux index to be less than 80 and K less than or equal to 3. Now the K index, or the SFI, the lowest is about 65, and the highest is several hundred. So that SFI being much, much closer to the lowest SFI value says we're around solar minimum. For propagation on the middle bands, 30, 20, 17, they're good throughout a solar cycle. Solar flux isn't a big issue, and we generally desire the K index to be less than or equal to 3. For propagation on those higher bands, 15, 12, and 10, they're best around solar maximum, where we are right now in cycle 25. We desire the long-term solar flux to be greater than 100 and K less than or equal to 3. So that gives us an idea when we see what the solar flux index is for the past couple of weeks, what bands may be open. For propagation via the F2 region on 6 meters, it's best in the fall, winter months around a big solar maximum. We're having F2 propagation via the 6 meter on 6 meters right now. It's all on FT8 because FT8 and the other digital modes have a sizable advantage over CW and SSB in how weak a signal can be detected. For 6 meters, we desire the long-term solar flux index to be greater than 200. And again, the K index less than or equal to 3. Do we ever want the K index to be elevated? Yes, the VHF types who like to work Aurora, they like to see K indices, 6 and 7 and higher even, and that'll give them Aurora contacts on 6 meters and even 2 meters too. Now remember, these are just the guidelines. What you can do for what's going on right now is check out the next slide. There it is. It comes from dxmaps.com. And when you go there, you can select a view. I selected a world view, and I selected the band. Kind of up at the top, you can see 10 meters is bold in that row there at the top. So this is a picture of 10 meters. I took this today and the data is from 2006 to 2010 UTC. So that's about around 2 o'clock your time. That's what was happening on 10 meters. The red indicates sporadic E was happening. That's why you can see some short contacts within the United States. And there are some longer. There's one longer path, one path into Northern Europe, and some paths into Western Africa and down into South America. Even one into looks like VK4, I think. Yeah, probably in Australia, and some into Hawaii. What happens is there are spots on who's working who, and they take that and plot the great circle path between the two stations working each other. And this is a great way to go look on 12 meters, 15 meters, whatever, and see what's going on. It even goes up into the UHF bands if you want to take a look, see who's working who. And that gives you a pretty good real-time indication if the band's working. If you see lots of lines on there, well, turn on a radio. You may have fun. There's some other methods similar to this. WhisperNet, you might have heard of that. PSK Reporter, the IARU Northern Cal DX Foundation beacons, and the Reverse Beacon Network. And there's some others out there. So instead of trying to take the solar flux index and the K index and translate that into what's going on, it's kind of easy just to look at one of these methods and see what's really going on. Okay, so let's take a look at what's going on over the next couple of years. We'll start with 160. Well, 160 is best at night around solar minimum, because that's when the ionospheric absorption minimizes. In other words, the reduction in signal strength is the least. But you shouldn't give up on 160 around solar maximum if you're a top band aficionado. Around the peak of cycle 23, which right now is still bigger than cycle 25, W8JI worked over 200 countries in all 40 zones on 160. He's got a really good station. That was part of the success story, but also he sat and kept his butt in the chair and worked people. And you can do it if you really want to. There's some other issues that are impacting 160. Of course, man-made noise from machinery and all our electronic devices. That seems to be going up over the decades here. And it's probably going to get worse as we do more. Atmospheric noise is a problem from thunderstorms. Now, those first two bullets, one way to mitigate that is use some what are called low noise receive antennas. And you can reduce the noise coming into your QTH because those antennas have directivity. In other words, they don't receive all around the compass. They're kind of like a Yagi, which has a main beam, and that helps reduce noise coming in from all directions. There's also, as we put more CO2 into the atmosphere, that's believed to result in more electrons at D and E region altitudes. That's where absorption occurs. So as CO2 goes up, we get more absorption, and that doesn't help 160. Okay, here's a summary for the HF bands for the next couple of years. One thing you should be aware that the maximum usable frequencies in the northern hemisphere decrease during the summer, resulting in degraded propagation on 15, 12, and 10. And you can see what happens in that Excel plot. That's a plot from K9LA to England, G, at 1500 UTC in all 12 months at 3 different solar cycle magnitudes. You could see in the summer months, the MUF is lower on that path, and it's lower on all the paths in the northern hemisphere. But when we get to the fall and winter months, that's when the MUF really increases and gives us great propagation. You can see that November and December on that path are really good. The MUF gets up to 40 megahertz, and that's about where we are right now in cycle 25. So in the fall and winter, the higher bands, 15, 12, and 10, are excellent for worldwide propagation. The middle bands, 30, 20, 17, should be great for the next couple of years. And the lower band should be very decent at night, 75, 80, 60, and 40. What about 6 meters? Well, over the next couple of years, sporadic E is important. We should expect it in the summer months, in June, July, and August. There's a plot of probabilities versus month. For example, in June, you can see that lower green, that's late morning. There's another green above it, that's early evening. That's probabilities of sporadic E on 6 meters. That's 2 years of data. They pretty much agree. You can also see there's another peak in December, which is only in the early evening hours. So hopefully we'll be seeing some sporadic E. Well, I think we may have seen some already by that DX maps. And we'll probably see some in December, hopefully, too. That'll help the 10-meter contest, maybe. Although 10 meters should be pretty good in December because we're at solar maximum in a winter, winter month. Terrestrial weather appears to have an impact on sporadic E. G3YLA over in the UK, he's a retired BBC weather forecaster, and he's looking at terrestrial events that seem to trigger sporadic E. So that's an interesting thing to follow. Of course, space weather has a big impact on F2 propagation. When we have lots of sunspots, lots of solar flux, that means that we have lots of EUV, and that's why the F2 propagation is best in the fall and winter. You can see that from that plot on the last slide. And right now, cycle 25 is bigger than 24, and that's really helping. And also FT8 helps with its ability to decode weaker signals. How about 2 meters? Wow, we're getting up there. For all intents and purposes, 2 meters is not affected by space weather. In other words, weather outside our atmosphere. The biggest impact of 2 meters is terrestrial weather via tropospheric ducting. That can cause very long distance contacts. There's a URL there. It's called the Hepburn Tropo Forecast. I pulled it for today at 18 UTC, which it's noon your time. And I selected the view that had mostly the Caribbean in it. You can see Texas is at the top left. And you can see the color scale indicates what the probability is of tropospheric ducting. Right there off the southeast coast of Texas, there's a pretty strong probability, but of course there's probably not many stations in the Caribbean. So maybe by some wild luck, you might have some tropospheric ducting into Florida, maybe, who knows? Okay, here's some references for propagation. The propagation chapters of the ARRL handbook and the ARRL antenna book. The ARRL's book, Here to There, Radio Wave Propagation. Bob Brown wrote a book, Little Pistol's Guide to HF Propagations. It's out of print. Bob is a silent key, but it's on my website at that URL there, at that link. CQ just updated their shortwave propagation handbook from I think it was 1995. So it needed an update. Unfortunately, CQ went under, so I'm not aware of where you can get any of those. So that's the way it goes. K9LA, he's the chair of the RSGB's Propagation Study Committee. He wrote a book called Radio Propagation Explained, and there's a link to go get it, or at least look at it. And of course, my website, K9LA.us, has a lot of stuff on propagation. So here's the summary. Cycle 25 has surpassed cycle 24. Yay! It may get up to an average cycle, like cycle 23, and that would be great news for 15, 12, and 6 meters. We'll probably see good propagation on 15, 12, and 10 out to about 2027, and then it'll start falling off. We'll see 6 meter propagation via the F2 region out to that period also. If cycle 25 gets even bigger than it is now, and we may still have propagation into 2027 up till 2028. We'll be at solar minimum probably around 2030. That's a best guess right now. So get on the air now and have some fun. And don't forget sporadic E in the summertime. Maybe next summer will be a little bit better. So that's all I had, George and Mike. If there are any questions, I'm sure try to answer them, that's for sure.
Fascinating presentation. Thank you, sir. Just got one quick question. A little controversial at first, but it turned out okay. Do we think we're going to get any good information from the HARP project now that it's been transferred to the University of Alaska?
Well, they've had their listen forum sessions and all that. I wouldn't hold my breath. Okay.
Yeah, I know it. Yeah. But there was a lot of science generated. It would be nice if we could get some of that data, though. But
yeah, it's all at high latitude, which of course we certainly could use more of that, because our propagation predictions don't model the high latitude ionosphere because it's so dynamic and changeable. So there may be some data in there, but we'll have to wait and see what they do with it.
I occasionally will watch on YouTube the Space Weather Woman.
Yes.
And she'll show like a globe, and she'll say, refer to high latitudes, mid latitudes, low latitude, and I can't tell by looking at the picture what she's talking about. What does she mean by high and low and mid?
Well, that's the latitude and longitude.
Yeah, but like in Texas, we're around 33. Is that mid?
Yeah, that's I'd call that kind of low. And then around that, then maybe 35 to maybe 55 is mid latitudes, and then above 55 is the high latitude. And of course, the the ionosphere is most robust in around in the equatorial regions, which are low latitude. And as you move away either north or south from the equatorial regions, the maximum usable frequencies go lower. So one of the things I notice all the time is I see you guys down in the southern states working stuff. I can't even hear it. And that's because you're taking advantage of being closer to the equatorial ionosphere.
That's interesting you say that. I have a buddy up in Illinois that,
yeah.
that he'll send me, oh, here's this DX station. And I'm like, it's hiss for me.
Yeah.
So that's interesting what you said.
Yeah.
All right. I think that is it.
Okay.
Again, thank you so much. This was just an absolutely wonderful presentation. Much appreciated.
Okay.